I was once told by a wise person that you should never agree to give a talk if you're in the last session of the last day, and you should never go to a meeting in Las Vegas in July. So my name is John Garrick. I'm not a chemist or a chemical engineer or a materials scientist or a neuroscientist or a policy analyst. So why am I here? Well, one reason I'm here is because I was invited by Ray Weimer, and I always like to go to a meeting with Ray Weimer because it gives me the comfort of not being the oldest one in the room. But I am pleased to be here, and I hope I have a few remarks that are of interest to the group. I want to acknowledge my co-author, Bill Geckler. I decided to at least bring a chemical engineer into the process of developing this paper. Bill is an outstanding chemical engineer, particularly from the point of view of doing safety-type investigations. I intend to cover three topics. One is a little bit about the QRA methodology, and the second is the presentations have helped in this regard, something about the nuclear safety experience in the chemical reprocessing field, and then a few ideas about how you would build a model for a reprocessing plant, a risk model. The real reason I'm here is because of a lot of experience we've had with respect to analyzing the risk of all manner of facilities. The methodology I'm going to share with you today, some of you are very familiar with it, has evolved over the last 4 decades. Our goal, the goal of basically the team that I've been associated with throughout my career, has to allow it to evolve to a general theory, a theory of risk assessment that can be applied to any kind of problem. And while the boundary conditions are very different and the phenomenological issues are very different, and therefore the risk team should be made up differently for each application, there are certain principles, certain process steps that have surfaced that seem to work well, whether it's a nuclear power plant, which is where we've had most of our experience, a nuclear waste facility, which we've had quite a bit of recent experience, a chemical plant, analyzing such far out things as the risk of importing certain animal species into a population where that species doesn't exist. Even did risk assessment in a cost-benefit trade-off of such transportation issues as the cost-benefit of going from special trains to regular trains, and some 50 or 60 nuclear power plants around the world. And so obviously you'd think that it would stabilize, and I think it probably pretty much has. And this is what I plan to do today. When I say it has sort of stabilized, it's kind of stabilized at the high level, at the process step. And what seems to work each time is the implementation of some 6 basic steps. And so our goal, our hope of this evolving to a general theory seems to be coming into fruition. First thing you have to do, of course, is understand the system that you're dealing with. And the biggest challenge of that in many instances is quantifying, if you wish, the success states of that system. And if it's a complex system, it gets particularly challenging. But you certainly need to know what represents an upset of any system. And so any departure from what you might define as a successful system is what you want to be able to expose. Number two, identify and characterize the sources of danger. We've done risk assessments where the risk measure was toxic chemical, or an explosion, or injuries, or fatalities, or disease, or almost any thing that was of particular interest to whomever we were doing the risk assessment for. In this case, it's very easy. We're talking about radiation. Develop what can go wrong scenarios and damage states. The methodology that I'm talking about is sometimes been referred to as the scenario-based approach to risk assessment. And so the cornerstone of the whole analysis is to develop the scenarios that represent as complete a set as you can develop of the things that can go wrong with the system. And then the mathematical part, the development of the scenarios being the creative part. The mathematical part is the quantification of the likelihoods of the scenarios, and the end states of the scenarios are the damage states. So when you quantify the scenarios, you quantify the damage states. And then even after you have the likelihoods of individual scenarios, which is an enormous amount of material, especially in the case of some complex facilities. And the number of scenarios may vary from a few to millions, just depending on how the model proceeds and how you've designed the risk measure that you want to compute and the level of detail you want with respect to the components and systems of what you're analyzing. And then, so you need to have a means of assembling those scenarios into an integrated or complete statement of risk. And you want to do it in such a way that you can backtrack and provide some very important outputs with respect to risk management. Such outputs as the relative contribution of issues that are contributing to the risk. So the cornerstone of the process are these basic principles. And one thing I'd like to point out is that, of course, the reactor safety study represented a turning point in the way we think about nuclear safety. But most of the internals of this methodology were developed in the private sector. The first big boost we got of my company many years ago was we dominated the risk assessment business in the nuclear power field. Our little team, and it was a little team, we had about 150 employees total. We were responsible for something like 45 U.S. plants and another 10, 15 international plants. And we just couldn't, almost couldn't keep up with the business during the 70s and the 80s. And then when the NRC got in the business, things changed a little bit, because our whole thrust was to what we called full scope risk assessments. We indeed wanted to quantify the health effects. And while there was lots of grumbling and grousing in the business about the inadequacies of the models, particularly the health effects models, with what we had done with respect to uncertainty modeling, we felt confident that the amount of information we could get would be enormously beneficial. So this is what is the backbone of the approach, the triplet definition of risk. This started in my PhD thesis, which was really given substance in 1981 with my colleague, Stan Kaplan, who, by the way, just passed away from Alzheimer's disease. When we published the first paper in the first journal, in the Journal of Risk Analysis, which was, by that definition, a quantitative definition of risk. Scenarios are the foundation. cradle-to-grave scenarios from initiating events to damage states, or if you wish, from initial conditions to damage states. And then the thing that we spent the most analytical energy on was our uncertainty models. We were really the first to put uncertainty in our fundamental risk models, as not as an afterthought, but as an inherent feature of the modeling process. And then we did something else. We adopted what I would call an engineer's definition of probability, not a classical definition, not a frequency limiting definition, but a definition that was very simple, but enormously helpful. And that was that we even considered the idea of not using the word probability, but rather using the word credibility. But we decided we'd leave it as probability. And that definition, of course, is just simply the credibility of a hypothesis based on the supporting evidence in the form of a number from 0 to 1. And then, since Bayes' theorem embodies the fundamental rules of logic and plausible reasoning, we became very Bayesian and had to be sure that all of our probabilities obeyed Bayes' theorem. So this was the process. Now, what do we mean when we talk about the triplet definition of risk? Well, that could be a short course in itself, and it has been in the past at MIT and at UCLA and other places. But at a high level, this is what it's all about. When we ask the question, what is the risk, we're really asking three questions. And they are, what can go wrong with our system? And the system can be a natural system, or it can be an engineered system, or it can be a social system. And if something does go wrong, how likely is it? And, of course, what are the consequences? Now, there's been a tendency over the years, as people have referenced this paper or this approach, to want to add other bullets. For example, another bullet that you'll see in the literature is, what are the uncertainties? Well, that's embodied in the second bullet in how you define your likelihood function. We always include uncertainty. And they also add the bullet sometimes, take corrective action. Well, that's not a risk assessment action, that's a risk management action. So we tried to keep it very clean, very compact, and built the analytical infrastructure around that. And so this is our notation that we've adopted for what we mean by risk. The inner brackets really enclosing the triplet, the outer brackets implying the set of, and the subscript C implying the complete set of. Now, of course, you don't always find the complete set, but we found that we can have very good luck at getting the mostly important ones. So let's go into it a little bit and just ask ourselves, what process do we go through to structure the scenarios? And it really, the 6 steps that I outlined for you tend to collapse into 3 major analytical activities. The first one is the middle one, understanding what the system is. And of course, something we learned very early was that the more you can linearize the system, the better off you are, such that in a system that's ABC2, or 1, 2, 3, 4, that 1 leads to 2, leads to 3, and so forth. In other words, you try to cast the system, whether it's a natural system or an engineered system, into what the mathematicians might call a linear vector space. And you want to do that because it gives you the whole arsenal of matrix mathematics at your disposal. And that becomes enormously beneficial, which you can't do if your risk assessment is just fault trees, because a fault tree space is not a linear vector space. But an event tree is a linear vector space. And so you would like to have your model such that you structured it in a way that you can define the output states from each of those boxes. For example, in the nuclear power plant case, we had the plant model, and we had the containment model, and we had the site model. So the end states of the plant model were plant damage states. The end states of the containment model were the release categories, and the end states of the site model were the dose ranges. So that is where a lot of the risk assessments fall down, is that they have not taken the time that's needed to characterize just exactly what the system is. And the part of it that's often neglected is the part of it that turned out in the nuclear power case to be the most important, and that is the support systems. The one that's sometimes the most difficult, especially if it happens to be a terrorism risk problem, is the threat assessment. We sort of have adopted a kind of a master logic diagram. It takes the form of a fault tree where the top event is the initiating event, or an event that could just disturb the system at any part of the system. And the kind of information that you require in that is not just things like failure rates and so forth. It's whatever information seems to be relevant to leading to a threat to your system at any point along the sequence of the system. The most developed part of it, in many respects, is the vulnerability assessment. This is where we have the initiating condition or the initiating event, but we know that initiating event is that the facility is usually designed to intervene with the continued pathway of that initiating event, and corrective actions are built into the system. The ABC, et cetera, are the so-called intervening events, or the top events, and you need to incorporate them in the whole structuring of the scenario process. So what kind of threats do we consider? Well, I think everybody's very familiar with that, and I'm not going to spend much time on it. But there are two types of threats we worry about, and they are the internal, that is the threats that come from the facility itself, and external. Some are common to both. You can have a fire internally initiated, and you can have a fire externally. But these, you don't put limits on this. And every location, this list is different. And of course, you've got to also, as we have very much aware from the Fukushima event, to worry about collateral events, such as tsunamis from earthquakes and what have you, or tsunamis from asteroid impacts, is a big issue on the coastal cities. Now we categorize these threats into two broad groups, and this was done extremely well in the Yucca Mountain Performance Assessment. But we like to define disruptive events and nominal events and processes. Now, by disruptive, we mean something that happens that can cause a significant change with a very short time constant. And that is the usual expected events, such as severe storms, tornadoes. We just did a risk assessment of a radioactive waste disposal system in West Valley, New York. And it was quite amazing, the number of things that were unique to that site. And that's always the case, whether you have a high-pressure gas line traveling through the site, or whether it's in the approach pattern of a military base, or what have you. Nominal events are kind of what you expect to happen with respect to the facility These are usually aging effects, degradation effects. But very often you can develop an expression or, that represents their rates. Sometimes it's constant, and sometimes it's not. So, what about probability? It's a very controversial topic, but on the other hand, I don't understand why, because it's everything has a probability associated with it. And as I said earlier, what we took to be the meaning of probability was actually an extension of the famous professor at Stanford and Washington University, St. Louis, Ed James. And in fact, he's one of the reasons I got interested in this business is that my colleague and I, Stan Kaplan, attended a short course at UCLA put on by James and Myron Tribus. And it was just a great experience because here was a genius with respect to the Boltzmann equation, which was the cornerstone of my early work, saying that most of the way people look at probability is not very productive. And he sparked really a long-term relationship and what I would say a major contribution to what we're now tabbing as a general theory of QRA or PRA. And by the way, I take QRA and PRA to be the same thing, a quantitative risk assessment and probabilistic risk assessment. Bayes' theorem answers the question, how does the probability of a given hypothesis change with new information? Very powerful, very simple theorem, one that can be derived in 2 steps, and probably one of the most profound probability theorems that exists. And it really is the cornerstone of any risk assessment that attempts to quantify uncertainties. Okay, that's all I'll say for the moment about the methodology. Let me talk a little bit about the safety experience of nuclear fuel recycling plants. And I'm not going to talk much about this because you've had a pretty good dose of this in the last couple of days. But we know that there are no operating plants in the U.S., although there might be an argument that the H. Canyon at Savannah River is still doing useful processing. And let's hope it is and hope it continues. There are plants in France, United Kingdom, Japan, and Russia. Many of them are having problems and issues, and some of them are not even running right now. I guess the one that's the most successful is in Le Hague in France. Certainly it has by far the most experience. And as far as recycling plant incidents, all of the plants, whether they're the government plants or the private plant in West Valley, or the plants in the UK and China, France and Japan. And there are some plants in India, but nobody seems to know much about those. At least I don't. And I couldn't get the kind of information that was needed to really make any kind of assessment of them. But all of the plants, as indicated in that third bullet, experienced leaks and spills and releases and fires and resin fires and all kinds of little events. As far as I know, none of them were catastrophic. None of them resulted in fatalities. There's 2 outstanding criticality events, and one in Tomsk, Russia, and the other one in Tokamura, Japan. And they both involve the same mistake of moving unsafe material from a safe geometry to an unsafe geometry. And in the case of the Japan, there were 2 people killed in the accident. Perhaps the most devastating one, it was the waste tank explosion in Russia. And this was a case where the cooling system for the waste tank was not in operation. It was very high level waste, a lot of heat being generated, and it eventually dried itself out, and it's basically ended up being ammonia nitrate and acetates, and eventually exploded. And that explosion lifted the tank from a buried condition and caused what some media reported as lots of fatalities, but they were latent fatalities. It's very fuzzy on just whether or not there was any acute fatalities. But in the nearby communities did suffer from that event. The most high-profile event are the red oil incidents, and there were a lot of those. I don't think there would be in a new plant. I think that we'd be using diluents and other methods to keep the temperature and the pressure under control. But we had them at Hanford, Savannah River, 2 at Savannah River, Oak Ridge we had one, Canada, and Russia. And so these are the main things that seem to have happened in the reprocessing field. So let me go back to my original job of telling you how you might address this on a system, on a step-by-step basis. So this is the third part of my talk. So the first thing we say you should do is define the system. And we always spent maybe more time on this part than any other part, except in developing the scenarios. But unless you did this right, you weren't developing, you weren't going to have much success in developing the scenarios. So how do you go about defining the system? Well, you do a lot of things. I'm not going to walk you through, for example, a typical Purex plant flow sheet, because you've had that. I think Bob Jubin covered this the other day. But except to point out that process flow diagrams in a much greater detail than this are critically important to understanding the system. But there are other things that are just as important. And one of the things we found that's probably the most important data source was something we were denied in the early days, and that was maintenance data. It is amazing what you can learn from the maintenance data about the performance of your plant. But maintenance data or operating procedures are absolutely critical, and being able to think out of the box. One of the things I learned as a director of a risk assessment team over 2 or 3 decades was that you've got to think out of the box in the creation of the scenarios. And generally, I didn't have much luck with people we hired that had a lot of licensing experience, because they kept trying to think within the box of licensing, and that's not what we wanted. And you really want to think as fundamentally as you can about what can go wrong with whatever it is you're analyzing. And the other thing that we found that was critically important, that was not analyzed in a lot of detail in the early reactor days, and that was support systems. And in the case of a reprocessing plant, you have a lot of support systems. You have off-gas systems, you have high-level waste systems, you have acid recovery systems, you have cleanup systems, you have solvent recovery systems, you have and the usual process systems like instrument air, steam, electricity, and what have you. And those, you really need to look in the dark corners of those to have any great comfort that you have been comprehensive in your analysis. This was the biggest lesson learned probably in the nuclear plants, because everybody was kind of married to the design-based accident concept, the guillotine brake concept. And so what led to 3 Mile Island? A simple relief valve, and not good knowledge about the disposition of that relief valve at all times, and the support systems. What led to a lot of other accidents was the failure of the chilled water system in the separate and independent chains, a system that you can go back to the early reactor safety studies and you'll see it never mentioned. So these are the things that can trigger things that can cascade, and that's why the scenario thought process is so valuable. One thing I forgot to mention, I said I was not any of the disciplines that seemed to be relevant to reprocessing. I was a little bit maybe shortchanged there. I had an experience with reprocessing that I don't think anybody in this room had. And I was on the startup team, and now I'm revealing my age. I was on the startup team for the Idaho Chemical Reprocessing Plant. But I wasn't hired for process work. I was hired to worry about the physics problems associated with that plant, and namely, mostly criticality. And it was the first, we put together the first criticality team for the site, and we not only had the criticality concerns about the plant, the chemical plant, but the reactors, and we even interacted with the Navy people, and certainly the EBR people. It was an exciting time, because everything we did was the first time. And when we put the product of the plant through its first paces from a radioactive standpoint, it turned out that the product was hotter than hell. And what do we do about that? Because nothing seemed to come out the way it was supposed to. Well, they put together a team of about 6 of us and said, fix it. And I don't think this is what you could do today. So we kind of slept with this system for about 12 weeks. First, we had to develop what the culprit was. I think Ray will know what that is. We discovered that for some reason or another, we weren't scrubbing out a couple of the key fission products, one of which was ruthenium-106. And so we simultaneously were doing distribution coefficient studies and height of transfer unit studies and all these chemical engineering exercises that I was learning as a very, very young and green scientist. And but we did put a team together that came up with a tail-end process based on precipitating out the ruthenium with an H2S process, H2S-based process, although we had to use a cupric ion to make sure that the precipitation actually took place. And we cleaned up the product. And we developed, designed, built, and processed that product in a period of about 7 weeks. And that was a great experience. We don't see a whole lot of that kind of activity these days. But anyway, this is just to tell you when you design, when you are trying to define the plant, that you really need to spend the time that's necessary to do it. And in most cases, our risk assessments were pretty expensive as a result of that. I remember meeting with the CEO of Pacific Gas and Electric. And he says, we want you to do a PRA of Diablo Canyon, but we don't want you to bother any of our staff. And I had the guts to stand up and say, well, and you don't want us. We have to involve the senior reactor operators in the process. They know the plant better than anybody. And just like at NASA, they asked us to do a special study on the space shuttle and later on the space station. And I kept getting these presentations from people And I said, how come I don't see more emphasis on the scenarios of what can go wrong? And they said, oh, that's somebody else's problem. And so they invited me to attend a training session of the astronauts. And here they were going all through these scenarios. This is what structure can do for you in terms of being an obstacle. And I went back to the safety people. I said, why aren't you doing what they're doing? Why aren't you analyzing each of those scenarios? They said, well, that's not our, what was the word? It's not our requirement, or some such thing. So anyway, I switched from working with the safety people to working with the astronauts. And that was a great experience because they thought the way we were thinking in terms of the shuttle and how it could perform. We were looking particularly at the auxiliary power units because the auxiliary power units in the space shuttle are not auxiliary at all. They are absolutely essential. You have to have them for every operation on the shuttle, from thrusting the main engine to all the control surfaces, to deploying the landing gear, to you name it. So that became pretty exciting because our little team would be working on a scenario. We'd call up, and we now had some actual scenario or astronaut contact. And they'd say, oh, I need more flying time. I'm coming out and work with you for a couple hours. And that was a great experience. And we built a kind of a first-of-a-kind model on the risk of losing a shuttle as a result of failure of the auxiliary power unit. Now, they had triple redundancy, but it really wasn't triple redundancy when we started examining it. It was more like they had 1.5 rather than 3, because the real reason was because they had not given a whole lot of emphasis to what we had commonly referred to as common cause failures. But that resulted in some real changes in thinking and increasing acceptance on the part of NASA of probabilistic approaches, because they were really down on probability. That all is rooted back, way back to about 1956 or 7, when GE was asked to do a probability analysis of getting people to the moon and back, and the number they got was very low. And that soured the agency, and it took a long time to overcome that. Now, interestingly enough, they have a PRA group in headquarters. They happen to be headed by 2 former nuclear people. And I'm on a National Academy committee right now looking at the risk of astronauts getting cancer from deep space flights. So we're making progress there. So this is what we mean by a success diagram. We're not going to analyze each one. I mainly wanted to point out the process we go through in the development of what is called a success diagram and the linearization of the whole facility. We will talk a little bit about box number 6. So if we decide we're going to analyze one of the boxes, then we turn up the microscope on that box. In this case, I went one too far. In this case, we decided we'd look at the concentration and purification of uranium and plutonium nitrates and ask the question, how would we analyze that? Well, this is what we would do. We would linearize it first, and what we're talking about here is that in order for the evaporators to perform their intended function, and without the high risk of a red oil incident, first have to make sure that the TBP has been removed, and second, that the evaporator feed analysis is indeed performed and appropriately acted on. Thirdly, that the evaporator temperature control is keeping the temperatures below the prescribed threshold temperature, maybe 120 degrees, and that finally the evaporator off-gas pressure control is at its intended levels. And so this is, we really try to decompose the system into a point that it's manageable from an analytical standpoint, and that it's useful from the standpoint when you're dealing with the people that really understand these, how these things work, that they can interpret what we're trying to do. Okay. Step 2, identify and characterize the sources of danger. Well, we can get through this one in a hurry, because here we're only interested in radiation, and others are sometimes much more complicated than this. So, all right, what can go wrong scenarios? As I said earlier, this is the creative part of the work. And this is where we needed the senior reactor operators. This is where you need the senior operators of any chemical plant. And this is where you need to interact with the maintenance people and the designers. But you've got to be careful with the designers, because what we found in collecting data from designers, there's a tendency to be a little biased towards the reliability of the system. And so how do we go about doing that? Well, the tool that's been most often used is the inductive logic model, or in the form of an event tree. And so here where we have A, we're really talking about the box that I showed you earlier. Is the answer is, has the TBP been removed? If the answer is yes, then you go to the right. And if everything is yes, if all the answers are yes, then that represents the success state. And if any of the answers are no, then you go downward into the vertical state. And you can represent any single scenario with a Boolean equation. And the A is that it's successful, and A bar is that it's not successful. So this is an enormously useful structure within which to think, because we can represent this whole matrix with a simple operator. And we can do diagonals on that operator and answer the question, given a certain input state, what's the likelihood of a certain output state? And that becomes an extremely useful piece of information. So we don't just calculate the risk. We really create the superstructure or the infrastructure of the whole process. We put some information in this one, and this is my token slide that you can't read. But it's done just to kind of illustrate how the process works. And except for the last 4, the output state, the damage state, is pretty much a feed that's off spec, and it's very correctable. But down from S13 to 16, you get into scenarios where you had more than one top event not performing its intended function, and you start to get problems like fires, and eventually something like an explosion. And of course, the red oil event is simply the distaste that organics and nitrates have for each other, and especially at elevated temperatures. And so if you have a TBP with its diluent like kerosene or dodecaine and uranyl nitrate or plutonium nitrate coming together at elevated temperatures, you get a degradation that, if uncorrected, creates a lot of gases, non-condensable gases, and the products include a lot of reaction products that can be very corrosive and sometimes explosive. So this is the type of information that you'd get out of the scenario. Now, as far as the quantifying the scenario, step 4, this is the most fun to us that studied applied mathematics and physics and neutron transport and what.
Yeah. I have a question. In your eventually all the knots you have there is any condition or probability that happen, or all of them supposed to be right or wrong?
Oh, what you're saying is, is it a binary system? And
yes,
generally we,
because
yeah.
There is a lot of what if,
sure.
What if you can get out of the box. So
sure.
The question is,
No,
yes
no? Well, the answer is it depends on what you're looking for and the model. You don't have to have just two states. You can have multiple states. You can have degraded states. You can put that in the event tree as well. In most cases, what you do is you treat all of the conditions under which you can get failure, and that may be multiple states, as one state. That's why it's so important to put the time that's needed into defining the success state. But no, there's no restriction on the mathematics. You can calibrate different states and analytically analyze them. Okay, so how do we analyze this? Well, we calculate our credibility factor, probability distribution at each point along the way. In the event tree, you first have to have the probability of the initiating event, and then you have to, at the split fraction or at the branch point, have the probability of it going down rather than across, and so on. And you have to, and the way we usually do this is we usually adopt frequency as the measure of risk, but we also know that that frequency has uncertainty associated with it. So we put that frequency in a probability distribution, and that's the PDF. Then we need to convolute the event PDFs into scenario PDFs. And that's just probability arithmetic, usually done by Monte Carlo sampling or some other sampling method. And then we have to somehow assemble those results into frequency of exceedance curves, or the more esoteric label that Mike Vogel used, the complementary cumulative distribution function. But the complementary cumulative distribution function has sort of surfaced as the classic risk curve. So we go back to our event tree, and this sort of illustrates the process. The A, B, C, D correspond to the success boxes that we showed earlier, and we pick any path we want. And of course, what we end up doing is quantifying all the paths, and we can. But if we pick the highlighted one, then on the lower left there you see the Boolean expression for that. And then, of course, the frequency version of that follows directly from that. And so now we have a Boolean equation for the frequency of occurrence of that scenario. And since that end state of that scenario is the damage state, we also have the frequency equation for that damage state. We will, in a few moments, talk about what the next step is after you get the Boolean expression. But if you pick one of the branch points, what you usually then do is another type of diagram. In this case, it was a fault tree, is used most often, although not always, to quantify the branch point. So the branch point that says feed analysis fails to prevent TBP in the evaporator field, well, that can happen only if analysis fails to detect the TBP, or the operator fails to send the feed back, so to speak. And then you can kind of work your way down. The diamonds tend to indicate that it needs further development. The basic events are usually denoted by the circles. And of course, you have transfer points. Some part of your fault tree down below may be applicable to, with respect to a feedback loop. And so here's the one for the evaporator temperature control. You know, the whole issue is a race between the evolution of heat and the dispersion of heat. And if you don't keep ahead of that race, then you do get the formation of gases and pressure and ultimately a possible explosion. Okay, now back to the quantification. This is basically probability arithmetic. So the path that we had highlighted is illustrated here. We started out with our scenario Boolean equation, and we transformed that into the frequency equation. And then we, on the basis of all the supporting evidence that we could get and keeping up with it through Bayes' theorem, we developed the probability density functions for each of the branch points and the initiating condition or initiating event. And it's based on whatever evidence you can find. And that evidence doesn't just include failure rates, because sometimes you don't have much going for you there, but it's expert judgment and experience and whatever seems to be relevant. Okay, the next step is the steps 5 and 6, because my only purpose here was to illustrate the process, not to share with you a comprehensive analysis. If you want to go on West Valley's website and see an analysis of how this was applied to a waste disposal facility, that's easy to do. It's about a 700-page study that was done in 3 months. And I remember my colleague at Sandia couldn't believe it. When he was a reviewer of it, he was astonished that what we were able to do. And I think that's primarily because we have been doing it for a long, long time, and for all manner of things. We even analyzed the risk of a pickle factory being successful in being able to generate or produce a certain quality of pickle. My colleague, Stan Kaplan, worked for 2 or 3 years with the Department of Agriculture to bring this technology into the food quality business. So I'm about done here. So these are the 2 principal displays that you'll find if it's a quantitative risk assessment. And what I mean by that, if it's a risk assessment that embraces the concepts of the uncertainty sciences. If it's a specific event, like a specific level of damage or a specific dose, the PDF is the way to do it. And all this portrays is that if the area under the curve that's crosshatched is 90% of the area, then what that curve tells us that we are 90% confident that the frequency of occurrence of that event is between phi1 and phi2. As to the integration process and the accumulation process, we go to a different kind of structure. And that one is achieved by taking all the PDFs of all the scenarios and accumulating them from the bottom to the top. First you have to arrange them in order of increasing damage and create what we referred to earlier as the frequency of exceedance curve. Now, this is a very useful curve, and it took us a long time to get the WIP format in this way, and we even had some trouble in the early days of getting Yucca Mountain. And I was in 2 different capacities. In WIP, I was on the National Academies Committee on WIP, and for a time chair of it. And in the case of the Yucca Mountain, my whipping platform was the the Nuclear Waste Technical Review Board, which is a presidentially appointed board in which I currently chair. But this curve really is a powerful piece of information. This one is useful with respect to individual scenarios. And then there's a whole raft of other things that go with these results, the most important of which is the importance ranking of all the contributors to the risk. That is really turns out to be, and that was just enormous eye-opener in a lot of these facilities, and including nuclear power plants. So I think that's about all I have that I want to cover. I have the usual conclusion side, which says nothing much. But the business has matured, both from the standpoint of the government's use of PRA and its extensions of the WASH 1400, the Rasmussen report. By the way, Rasmussen was one of our board members on my company. I didn't say anything about my company, but I had a company from the early 70s until I sold it in 1997. And that little company had something to do with every nuclear plant in this country. Sometimes it was a very small thing, but we were heavily involved. So we didn't do any government work until much later. NASA broke the ice. They came to us, and then in the waste field, it's been pretty much all government. So that's it. Thank you. Thank you very much. Are there any